Welcome back to The Explainer. Okay, let's jump straight into it. Today we're talking about bridging that massive gap between abstract physics and hands-on engineering. Imagine taking the vast, complex mechanics of the universe and, well, shrinking the whole shebang down to a plastic desktop grid. We're diving into the sheer elegance of analog computation. It's where the continuous mathematical functions that govern our world aren't recreated through lines of code, but through raw, physical electrical behavior. By translating dynamic systems into circuits, we get to observe complex phenomena unfolding right there in real time. It completely shifts how we look at the foundational rules of reality.
So I want you to ask yourself, is it really possible to replicate the grand physical reality of our universe right on your desk? Like, can the massive forces governing the cosmos be accurately mirrored sitting right next to your morning coffee? It's a bold question for sure, but it's literally the heart of analog simulation. For decades, physicists and engineers have known that the equations describing, say, a falling object or fluid flowing through a pipe can be mapped identically to electrons flowing through a circuit. We're not talking about a digital approximation here, no ones and zeros. We are talking about a continuous physical analog that behaves exactly like the macroscopic world, just in a completely different medium.
Section 1. The universe on a desk.
The entire foundation of our explainer today boils down to this one incredibly ambitious premise from our source material: replicating nature laws using electronic components on a breadboard. Think about how much ambition is packed into just 9 words. We aren't just tinkering with a few LEDs to make them blink. We are capturing the mechanics of reality itself in a highly controlled, continuous environment. When you set out to simulate physical laws this way, you're looking for a system that inherently obeys the exact same differential equations as the natural phenomenon you're studying. By tapping into the instant responses of analog circuits, you completely bypass the latency and quantization errors of digital computation. You're building a physical twin of the universe's mechanics, unfolding continuously, in real time.
Let's transition to Section 2, defining nature's laws.
Before we get too deep, we have to pause and wonder, what exactly are we replicating here? Taking these massive, continuous concepts, things like thermodynamics or fluid dynamics, and squishing them into a desktop environment means we have to isolate the specific mathematical rules that dictate how those forces interact. We all know reality is governed by systems of differential equations, right? Whether you're looking at Navier-Stokes for fluids or Newton's laws for mechanical motion, the real trick isn't just knowing the laws, it's finding a parallel physical system that naturally processes those exact same mathematical relationships without ever needing an algorithm to crunch the numbers. So basically, we're acting as translators. We're taking the invisible, abstract math of the universe and turning it into a tangible language we can control. Take a classic mass spring damper system. The differential equations governing its oscillation and decay, they are structurally identical to those governing an RLC circuit. You know, a circuit with a resistor, an inductor, and a capacitor. The math honestly does not care if it's describing mechanical force or electrical voltage. By spotting this isomorphism, we translate abstract rules into a physical electronic setup. This circuit isn't computing the equation, it's simply behaving according to it. It's a pure analog translation.
Which brings us perfectly to Section 3, components as building blocks.
This perfectly illustrates our core analogy. There's a direct one-to-one mapping here. On one side, you've got the vast abstract laws of physical reality, and on the other, you have electronic components stepping up as their tangible desktop equivalents. The mechanics of the universe are perfectly mirrored by electrical engineering. Want to model velocity? You look at electrical current. Need to model physical displacement? Measure the electrical charge. This mapping is exactly what makes analog simulation such a game changer. You're not just drawing a graph on a screen. You're sparking up a parallel physical reality where electrons enforce the rules of physics instead of mechanical gears.
Just like a mechanical system relies on mass, friction, and compliance, our electronic system uses specific hardware to represent those exact variables. Take capacitors. They store electrical energy in a field, acting precisely like a mechanical spring storing potential energy. Inductors resist changes in current flow, which perfectly models mechanical mass or inertia. And resistors, they dissipate energy as heat, acting exactly like physical friction or aerodynamic drag. So these aren't just off-the-shelf parts from a bin. They are the physical variables and energy translators of your simulation. By simply swapping a capacitor, you are literally altering the mass of your simulated universe. How cool is that? So the natural next question is, how do all these pieces actually come together? A pile of resistors and wires isn't going to do much just sitting there. To replicate a unified law of nature, these components need a foundation to interact on. They need a stage where the variables bind together to form a dynamic system. You have the actors, right? But they need a theater. In analog computation, exactly how you interconnect these components determines the specific differential equation the system is going to solve.
Let's explore that theater in Section 4, the breadboard canvas.
As defined here, in this specific context, a breadboard elevates way beyond a simple prototyping grid for hobbyists. It becomes a literal simulator for reality. It's a desktop sandbox utilized for dynamically modeling and observing the laws of nature through electronics. This is the matrix where your components finally get to communicate. Because it's a flexible, solderless environment, you can instantly alter the topology of a circuit. That means you can literally change the foundational rules of your simulation on the fly, experimenting with complex feedback loops without ever waiting for a custom printed circuit board to be manufactured. It is honestly awe-inspiring to think that a basic piece of plastic with some metallic clips inside can act as a microcosm. By plugging straight into this grid, we test and observe universal phenomena in real time right at our desks. You completely bypass the need for massive mechanical testing rigs or gigantic fluid channels. You can model a car's suspension system, the acoustics of an entire concert hall, or the thermal dynamics of an HVAC system, all within a 6-inch block of plastic. The breadboard strips away all that cumbersome mechanical logistics and just hands you the pure underlying math.
Okay, let's wrap this up in Section 5, Replicating Reality.
This elegantly breaks down the whole conceptual procedure, and it's remarkably straightforward. Step 1, you identify the natural law you want to study. Maybe it's Newton's second law, or the damping of a pendulum. Step 2, select your corresponding electronic components, mapping force to voltage and velocity to current. And Step 3, wire the breadboard. You are literally wiring reality into existence. When you apply a voltage step to that circuit, the resulting curve across your capacitor, if you're looking at an oscilloscope, is the exact mathematical equivalent of that pendulum swinging. You're watching physical phenomena unfold continuously. No digital code required.
Returning to that initial quote we looked at, doing all of this using electronic components on a breadboard does something absolutely vital. It democratizes science. It brings the complex laws of physics quite literally to your fingertips. It removes that massive barrier of needing multi-million-dollar labs to observe fundamental universal behaviors. Historically, right, analyzing these dynamic systems required massive analog computers that took up entire rooms. Today, the core principles of those giant machines can be rebuilt on your desk. It empowers anyone with a basic grasp of circuit theory to deeply comprehend the invisible forces shaping our world.
And this brilliantly illustrates the journey we've taken today. We've seen that the grand, natural physical laws governing the macro universe can indeed be perfectly mirrored by a micro-simulation. The complexities of reality are neatly contained within those electronic breadboard circuits. But this parallel isn't just a neat parlor trick. It's a profound reminder of the universality of mathematics. The universe runs on a surprisingly consistent set of rules. Whether those rules govern the orbit of planets, the flow of a river, or electrons moving through a wire, the math remains exactly the same. And by leveraging that consistency, we gain incredible insight into the architecture of reality itself.
So, to wrap up our explainer today, I want to leave you with one final provocative thought. What law of nature would you replicate if you had the components in front of you right now? If the mechanics of the universe can literally be mapped onto a desktop grid, what invisible forces do you want to make visible next? The tools to simulate reality are probably sitting right there on your workbench. Keep questioning, keep building, and I hope this completely changes the way you look at the electronics right in front of you.